This video is a brief introduction to electromagnetic induction. So here we have a magnetic field that is pointing into the page, and a conductor is placed within this magnetic field. We then move the conductor to the right. Whenever there are moving charges within a magnetic field, they feel a force. We know this from the right-hand rule that we covered. So applying this right-hand rule, we point our fingers into the page and our thumb with the velocity, and our palms face up. This means that the positive charges feel a force up and the negative charges feel a force down. And this causes a separation of charges within the conductor. The charges that are separated eventually start to repulse each other since like charges do not want to be close to each other. Equilibrium is established when the magnetic force cancels the electric force of the repulsion. And at this point, the electric and magnetic forces are equal. The force because of the magnetic field is equal to QVB, and the electric force is equal to the charge multiplied by the electric field within the conductor. We can cancel Q on both sides, and we are left with the velocity multiplied by the magnetic field is equal to the electric field. We also know that voltage difference between 2 points is equal to the electric field multiplied by the distance between the 2 points. So we can then expand this equation to find that the induced voltage between two ends of a conductor that is moving in a magnetic field is equal to BLV, where L is the length of the conductor. So let's do an example using this new equation. How fast must a 2-meter long conductor move through a magnetic field of strength 0.6 teslas to induce a voltage difference of 10 volts between the two ends? So we know our voltage difference equation is BLV, and the magnetic field is 0.6, the length is 2, and the voltage difference that we want to achieve is 10 volts. So we plug in our values here, and when we solve, we see that this must be traveling at 8.3 meters per second.